this is Unit 1, Chemistry Basics, and by basics I mean very basic stuff that you've had before. Some of it may be new, but for the most part this is very, very simple stuff. First, here's a list of the elements that are most common in all life forms. I want to focus your attention mainly on a couple here that are more common than others. These six elements make up this acronym SPONCH. Maybe if you're more daring, the acronym SCHNAPS. Either way, it is these elements are the ones that we're going to be dealing with most when it comes to what make up the macromolecules in your body. You can see there that some are even more prevalent, like calcium, potassium. They're very important also. We will talk about those this year as well. But these single letter ones are the ones that I want you to spend a lot of your time thinking about. So the most basic element of chemistry is an atom. Atom is the smallest unit of matter. The atom still contains all of the properties of an element. You know, this is an atom of helium here with 2 protons. So this is still helium, even though it's really, really small. The atom is made up of several components. You have the protons that are the positive pieces, the neutrons here, which are these neutral pieces. They do not have a charge. Neutrons, protons, and then swarming around the nucleus are the electrons, and this is usually the type of diagram that you see with the electrons kind of floating around the outside. The one on the left here is probably more accurate because the electrons are just all over the place all the time. Now the electrons, here's just a couple of other terms just to clear up some stuff, and then we'll talk a little bit more about electrons. A molecule is when you have 2 or more atoms bonded together. They can be the same, they can be different. For instance, here's an oxygen molecule, O2, makes sense. Some molecules are different, H2O. We'll look at a lot of different kinds of molecules. Back to electrons. So going back to this picture, notice the electrons are sometimes near the center, sometimes they kind of venture out here. Why do they do that? Well, I think this picture shows us electrons directly represent the amount of energy that is in an atom. If the electrons are spinning quickly, if they're rotating quickly, then there's probably a lot of energy. If they're not rotating quickly, then there's really not. Then if they're rotating quickly, there's a lot of energy. If they're not rotating quickly, maybe there's less energy. Think about it as if you had a string with something tied on the end of it and you were swinging it around your head. If you were swinging it pretty quickly, it would be as far away as it could get from you, from the string, right? And so think of an atom. The atom really loves, think of an electron. The electron really loves the nucleus because of that proton. This positive and this negative love each other. However, there's so much energy swarming around that it causes this thing to go wide of the nucleus. If there's very little energy, then it's closer. If there's a lot of energy, then it's further away. And that's kind of what you see here with this picture. So you could, let's say you had a baseball tied to a string and you were swinging it around your head. There is a sense in which you could spin that baseball so quickly that you would not be able to hang on to it anymore. Now, that would be hard, but you could maybe do it. Or you could spin it so slowly that it wasn't actually spinning anymore, it was just kind of stuck to you. Alright, so electrons behave in this way as well. Now some electrons always stay close, but some electrons are always out here. And the ones that are towards the outside, the outermost electrons, are called the valence electrons. These are the ones that are probably spinning the most, have the most energy, and also could be let go of easier. And so here's some examples of valence electrons. Hydrogen only has one electron, so it has one valence electron. But you notice with some of these bigger atoms that have a lot more electrons, they still have valence electrons, even though there's more electrons to be had. And this represents both the idea of potential energy and kinetic energy. Kinetic energy is energy that is moving. That potential energy is energy that is kind of stored up. All right. And so with electrons then, when those electrons in one atom interact with the electrons in another atom, you have a chemical bond. A chemical bond is just when two atoms join together through some sort of sharing or some sort of arrangement of those electrons. And we're going to look at some of the different kinds of bonds now. The first bond that we're going to look at is called the covalent bond. In the covalent bond, notice what's happening with these electrons. Well, this hydrogen only has one electron, right? Well, this carbon has a lot more than that. It has 6 electrons. It has 4 spaces in its outer shell. And so this carbon has room for each of these hydrogen's electrons. And the hydrogen is also taking part in the carbon's 4 outer electrons. And so what you have there is both of them are kind of hanging on to each other's electrons. And so in a covalent bond, we say that the electrons are shared, meaning that they're hanging on tightly to each other's electrons. This is the strongest type of chemical bond. And with that, it also represents the most energy, meaning there is a lot of energy in those bonds, and when you break them, it takes a lot of energy to break them. Now, some covalently bonded molecules while they do share their electrons, they don't equally share their electrons, and we call these polar molecules. So you could say the polar molecule represents the unequal sharing of electrons. What do I mean by this? Well, let's take this water molecule, for instance. This water molecule has 8 protons, and they don't look like that, but you get the idea. And it has these hydrogens have 1 proton each. There's a total of 10 electrons swarming around this water molecule, right? 8 from the oxygen, 1 each from the hydrogen. If you're an electron and you love positives, each one of these protons is a positive. Where are you going to be spending most of your time? Well, you're going to spend most of your time where there are a lot more positives. And so what ends up happening? The oxygen end of this atom, because this is a 3-dimensional structure, the oxygen end of this atom has a slightly negative charge. The hydrogen ends of this atom have a slightly positive charge. And so we call this molecule polar because it has these ends, these positive, negative ends. Another type of bond is called an ionic bond. An ionic bond is where, first of all, let's talk about what an ion is. An ion is a charged atom. What do we mean by that? Well, let's look here at this sodium. Sodium has 11 protons and thus has 11 electrons normally. Well, one of those electrons is a valence electron. It doesn't want to stick around. And so when that happens, when this electron, you can see it right here, when that electron leaves, all of a sudden sodium has 11 protons still, but only has 10 electrons, so sodium has a +1 charge. Look at chlorine. Chlorine's the opposite. It has an empty spot in its valence shell. All right, so normally chlorine has 17 protons, 17 electrons with no charge. But chlorine loves to pick up that extra electron if it can, not sodium. And so it will do that, giving chlorine a -1 charge at times. And so what does this do? Well, chlorine loves to take an extra electron. Sodium loves to give an extra electron, and so they're absolutely made for one another, and they will form a bond. Now, are they sharing electrons? No, they're just trading one back and forth. And so what we say of an ionic bond is they are transferring electrons, transferring that one electron back and forth. This is a strong bond, but not the strongest of bonds. When structures form ionic bonds with one another and there's no water around, they'll actually crystallize like you're used to seeing salt do. Only when they're dry, though, water actually pulls them apart. Now, another type of bond that we need to look at is the hydrogen bond. Hydrogen bond is an attraction between two polar molecules, right? Attraction between two polar molecules. How is that possible? Well, we looked at the polar molecule earlier with water, and we said that there's a slightly negative and a slightly positive charge there. Well, this slightly positive charge here on this water molecule is attracted to the slightly negative end of this ammonia, and they're not doing it. There's no electrons involved here other than the ones that are causing these slight charges, but there is this magnetism that is going on between these two charges. And so the hydrogen bond is like a magnet. It's relatively weak, but it's strong enough to stay together. And so because of that property, these are the most important bonds in biological systems. Bonds that can be broken very easily with very little energy, but that will also stick together without any fuss. And so we see these bonds used most prominently, I think, is how the DNA molecule is bound together at the middle. This is the use of hydrogen bonds. We'll spend a lot of time talking about these hydrogen bonds. And the last force that we're going to look at are interactions called van der Waals interactions. These are always temporary bonds. And a good way to think about this is when you rub a balloon on your head, that balloon builds up static charge in your head and in the balloon, and it causes your head and the balloon to be attracted to each other relatively temporarily, and then the balloon kind of falls to the ground. And the reason is because if this is your head and this is the balloon, what's going on here is you are causing these electrons in the balloon to kind of come over here. The positive parts of your face are here, and what's going to happen? Well, the positives of the balloon are going to move to this way because they don't like the positives of your face, and vice versa. And there's going to be a temporary charge or temporary attraction. Well, as those charges equalize, it's going to settle back in, and the balloon is just going to fall away. Well, you get the idea. It's going to just fall away. These are in our bodies or in your cells are most prominently featured in the interaction between like enzymes and substrates, which we will talk about enzyme substrate reactions in another video.